foremost, it's Lorenzo Orecchia from right now MIT Math, but I'm starting at BU in January. And this is joint work with Zaiwan Allen Tzu, who just changed his last name, so I got confused. And he's at MIT, and Zhenyu Liao, who's a student of mine at BU, even though I'm not there yet. And the title of the talk is First-Order Iterative Methods in the Design of Fast Spectral Algorithms. So let me give you a brief introduction of what we're talking about. We saw in the last few days the amazing power of this Laplacian paradigm. We have a lot of graph problems, and we can all, in some sense, reduce them to a number of computations of solution of a STD system. And max flow problems, graph partitioning, lots of different fundamental graph problems. The picture has been this one. And I'm kind of going to focus on what happens on this arrow. It's not trivial. How do you turn a maximum flow problem into an electrical flow problem? And what goes on here is actually my favorite part, because it's a very elegant interplay of discrete and continuous ideas. You do preconditioning, which comes from the numerical computing world, but you use a discrete object like a spanning tree to precondition. And what's been happening more and more in this arrow is the use of iterative methods from convex optimizations. We are really starting to leverage these methods and understand very well what they do. And here are the main example, probably the most famous and ubiquitous one, is multiplicative weight updates. That's been popping up everywhere, kind of, in TCS, not only in this specific framework. It's a very common technique. And it turns out that it's essentially an iterative method, as you will see. Gradient descent, accelerated methods, these are more advanced methods. Think of conjugate gradient, of Chebyshev method for solving system of linear equations. And then, like as Alexander, I guess, was supposed to talk about, but really didn't, interior point methods are kind of the frontier. And for the purpose of this talk, I'm actually going to focus on the first three of those, which can be thought as, they're actually called black box first-order iterative methods, because as you will see, this can be stated in a very simple black box framework. Interior point method is more advanced because it looks at the global structure of the problem at every iteration. So we're going to keep it simple in this talk. And yet, even though we are going to keep it simple, we'll see that these methods have an amazing power. And these methods are not new. We already knew about multiplicative weight updates. We already knew about gradient descent. And they had lots of applications already in the theory world and in algorithms before STD solvers and before the advent of the Laplacian paradigm. But now, and even as a proof technique, they yielded, for example, the QIP equals p-space result strongly relies on a version of multiplicative weight updates. So they're really powerful. But now they are really coming, they're really showing all their power as part of this Laplacian paradigm. And actually, for me, I don't tend to think in this way anymore. I really like to think in this way, where sometimes you don't even need to go here. Sometimes the combination, just understanding your first-order iterative method, is powerful enough to give you results that were not known before. For example, I'll briefly mention some results for packing LPs that were not really clear before we really started exploring this area. Okay. So the plan for this talk is that, I forgot to write this slide. So the plan for this talk is that first I will introduce what black box iterative methods are, and I will show you gradient descent, which is the simplest form of such a method. And then I will talk about multiplicative weight updates and their generalizations. And then I will show how by simply putting together these two bricks, you can get Nesterov's algorithm, which is the optimal method for smooth optimization, and we'll see what that means. And along the line, I've spent quite a bit of time on multiplicative weight updates, because I think there is kind of a lot of interest on how we can interpret this method. And I will show that the generalization of multiplicative weight update is also interesting, and it yields interesting perspectives in other problems. For example, in specification, sometimes you can do something which is like multiplicative weight updates, but with a different regularizer, and you'll see what it means, and get better results. Anyway, lots of preamble. Let's get going. What does it mean to be a black box method? It means that I'm optimizing some convex and differential function. I'm minimizing. And the only way in which I access the input is by querying a point x in my feasible set, and I get back the function value and the gradient. And my goal is to query a bunch of points, and then use somehow these queries to produce a new point, which could be, it could be one of the queries, or it could be an average of them. This last point, x out, has to be an epsilon approximation to the optimal value. And the question is, how many queries of this black box can I use? Michael?
Wait, so when you're saying you're saying you're black box with respect to f, but you're not necessarily a black box in any way with respect to x, the convex set being optimized.
Right now, yeah, I'm not.
Okay.
It turns out that throughout this, because I want to keep my methods very simple, x will be a very simple set on which optimizing is trivial. So x could be the simplex or the sphere, but in general, I assume that I can solve optimization. I have lots of power over x. So I wouldn't, if I solve a linear program, I won't put my feasible set here. I will somehow incorporate in the definition of f. That's a good question. So simple set x. So this model is particularly nice because actually you can prove lower bounds for this. It's so restrictive that you can actually prove information theoretic lower bounds. And it's also nice because when we want to design a fast algorithms, we want to do things that are very cheap. Every iteration has to be cheap. And this property that at every iteration we can really look at the input only in terms of the function and the gradient is a good way of modeling what it means for an iteration to be cheap, to be fast, to be a quick sketch of the problem. So let's see, how do we go about analyzing a black box model? We need two things. First, we need to somehow have a procedure, have a way to output this x out and have some upper bound on its value. But at the same time, if we want to have a theoretically sound algorithm, we also need to have some way of certifying that our final x out is close to optimum. So these are two separate goals we have, and these will be important in the course of this talk. And I will kind of always talk about a primal side or a primal problem in which we try to produce a point which has a good objective value, but also a dual side in which we try to prove a good lower bound on the optimum. And these will be kind of competing goals of our algorithm. All right. And last thing I need is what the assumptions are. We need some nice assumptions on the functions we'll be minimizing, because otherwise, in the most general setting, there is really little you can do. So there are two kinds of assumptions we'll use. The most important one is the notion of smoothness, which technically you can think of as the gradient being Lipschitz with parameter L. So if you move in your space by, to go from x to y, the gradient cannot change too much. It can change at most by the distance between x and y times L. And it's a good moment to say that throughout this talk, I'm going to use norms, and you may see primal and dual norms. If you are uncomfortable with it, just take all the norms to be L2, and everything will work. If not, then you're on your own. You know what you're doing. The kind of fundamental case you should think about, which is not L2, you should think of L1 and L infinity. And also the other one will appear, L infinity and L1. In some applications, actually, essentially all norms in between appear as well, but we will not do that. Okay, so why is this useful? We'll see that essentially the fact that the gradient changes smoothly will allow us to do something like gradient descent. There is another case which is more complicated and actually more common in our community because it tends to arise from combinatorial optimization problems, which is non-smooth optimization. So now what happens is that the gradient can change completely at a point. But what we know is that the gradient is never too big. So these lines here never become too steep, but they can change completely in a very small interval. And this actually makes things much harder. Essentially for the reason I said, that in this world, we can somehow predict what the gradient at our next step will be. And I will show that that's enough to make gradient descent work. And I will call this a primal approach. So in this world, we'll focus on decreasing the function value. In this world, essentially gradient descent doesn't work because if you're at this point, any kind of gradient descent algorithm that works has to use the norm of the gradient to make a decision about which step length to take. And if the function can change completely in a closed neighborhood, you have no idea of how far you should go along your gradient. And you may completely overshoot, or you may choose to move too slowly, and then you'll converge slowly. So in this method, in this world, in some sense, the idea of gradient descent does not work at all. And it's kind of amazing that there are ideas inside that work and that rely essentially on a dual approach. So you don't do gradient descent. What you do is you think of this gradient not as a suggestion in which to move your primal solution, but as a lower bound, as a hyperplane lower bound in the function. And then you're going to query other hyperplanes lower bound in the function, and hopefully you can put them together into a good lower bound. And the advantage here is that if you know that all the upper planes you query are not too steep, it's going to be easier to form this lower bound. But it's a completely different idea from gradient descent. It's a dual technique based on improving a lower bound. And I mean, it's actually, in some sense, symmetric to gradient descent. It's like doing gradient descent on the dual, but I am philosophizing. So the outline, again, I will first do the simple primal approach with gradient descent for smooth optimization. Then I'll do the dual approach for non-smooth optimization. And this has many names, has appeared, has been rediscovered many times. I will call it dual averaging. And it is a generalization of multiplicative weight updates. And it strongly relies on this notion of regularization. And within this part of the talk, we'll explore kind of, to some extent, the connection with online learning. Many of us have first discovered the idea of multiplicative weight updates while discussing online learning problems, like online linear minimization. Then we'll put, at the end, briefly, we'll put these two together to get a primal dual approach, which is optimal for smooth optimization. And in this slide, I also gave you a preview of what kind of running times we'll have, just to give you an idea that non-smooth optimization is the hardest one. So if you want an epsilon error, you'll need 1 over epsilon squared. Gradient descent, because you have this nice property, this nice smooth property, allows you to converge in 1 over epsilon. But for smooth optimization, we can actually do better by combining primal and dual ideas and get to 1 over square root epsilon. Any questions now before I go into gradient descent?
Yeah, Lorenzo, is 1 over epsilon square optimal for the non-smooth case in your black box?
Yeah, it is optimal, and it's, the same examples that are bad for multiplicative weight updates are bad for the non-smooth optimization setting. They're essentially randomly constructed linear functions.
What do you mean by optimal?
Optimal in terms of the asymptotic dependence between epsilon and the number of iterations. So square root t, epsilon will go down like square root t, and asymptotically that's optimal in the general case for non-smooth optimization.
This is assuming just the black box model?
Yes. And that's actually not hard to prove, just information theoretically. You can construct a family of inputs on which you have to spend that time.
In the non-smooth case, what's the dependence on rho?
Good. So that's a great question. In the most general setting, I believe it's rho squared. But there are, if you have just a bit of structure, you can often improve the dependence on rho quite dramatically. For example, for packing, you can easily get it down to, for LP, packing LPs, you can easily get it down to rho instead of rho squared, and you even remove it completely for packing LPs. So that changes more on the context. But epsilon squared is kind of used. It's much harder to overcome that. It's more inbuilt in the method. Okay. So gradient descent. So informally, when we think about gradient descent, we think about being at xt and taking a step in the direction of the gradient at xt. As John mentioned in his talk, this is really a special instance of gradient descent for the L2, for the Euclidean case. In the more general definition is that we are going to consider a linear approximation to our function at xt, so the approximation given by the gradient. And then we are going to minimize this linear approximation inside a certain ball around our point. So we find we have this kind of trust region. So we have this ball where we believe the linear approximation to be pretty good, and we pick the best point in this ball. And the radius of this ball, here I'm kind of hiding details, the radius of this ball can actually depend on the norm of the gradient. But this is the idea. And again, we talked already a bunch of times in this workshop about how quite a few of the recent developments in fast algorithms involve using gradient descent schemes which are not Euclidean. So I think John already showed this picture where this is Euclidean gradient descent because we are optimizing the gradient inside the ball, but in the max flow algorithm we use an L infinity gradient descent. So, sorry? Yes. Well, actually, I stole it from you. You stole it from Intat, and I think Intat made it, but we should ask him. So smoothness is kind of fundamental property that will also will also be important in the non-smooth case. So we should really focus a moment to understand what it is. So one way of defining smoothness is by how the gradient changes as you move from x to y. It turns out that this definition is essentially equivalent to the following, that you can upper bound the function value at y by a quadratic function, which is the function value at x, then the gradient approximation at x, and a quadratic term on y minus x. And this you just do kind of by integrating. In some sense, because the gradient cannot change very quickly, the function cannot shoot up all of a sudden. Okay, and so this will be, and I'm doing all of this for convex functions. The same ideas work for concave functions. So the smoothness will be defined the same way, and this sign will be different. You'll get that the point is at least, f of y is at least this quadratic function. So how does this help in a picture? The red line is our objective function, which we don't know. All we know of the red line is that we query this point. We have this function value and this gradient. And by using the smoothness property, this allows us to recover this quadratic function, which we know is an upper bound to our input. So the natural thing to do is to pick our nest update to be the minimum of this blue function. because that yields you the largest guaranteed decrease in objective. You don't know where the red function is. It could be exactly at the blue function, or it could be lower. But the best you can do is to go here. And it turns out that that's exactly what gradient descent does. And in the unconstrained case, you have a guaranteed decrease in objective, which equals this quantity, which you should notice depends on the size of the gradient. This makes sense because if the gradient is big and the gradient cannot change very quickly, you can take a long step and have a big decrease in function value. And this idea that large gradient is good for gradient descent kind of intuitively will be important later, because I already showed you that large gradient is kind of bad for the non-smooth case. The non-smooth case should be easier when the gradient is small, if you remember this dual picture I mentioned. And it turns out that in some sense, the essence between primal dual is that you want to argue that the primal does well when the gradient is large, and the dual does well when the gradient is small. In a very hand-waving sense. Okay. Right, so let's finish the analysis. Now it's pretty easy. We have a decrease in the primal objective. Somehow we also need to lower bound the optimum. And this is actually usually it's the more tricky business, because we don't know where the optimum is. And gradient descent takes a fairly naive approach to the question of lower bounding the optimum. What it does is it looks at the last hyperplane it queried, and it says, the function has to be above this hyperplane, and the best point can be, how far away can the best point be from me? I can just upper bound that by the diameter of my feasible set. And then what I get is that my kind of distance in objective value from the optimum has to be less than the size of the gradient times some notion of diameter. Here, it's the distance, but you can replace this with the diameter of the set. And now I have these two equations, which relate my improvement, my progress in one iteration, and my distance from optimum, and they both involve the size of the gradient. So I can trade off this term, and I will get a bound like this. And R squared is exactly this kind of notion of distance. And for the L2 case, it's just the distance from the initial point to the optimum. I take it as some notion of how big the feasible set is. And so the bound depends on L over T. So the smoother your function is, the smaller L is, the faster you converge linearly. And the 1 over T means that if you want to get epsilon convergence, you need 1 over epsilon iterations. And you always see that L and T, they always they have like the same units in some sense. So they will always come in L over T or square root L over T. Or okay. Any questions on gradient descent? All right. So
L and T have the same units?
Well, I'm saying that essentially in most bounds involving smooth optimization, you should expect L to always be divided by T, because you can change your function. You can double it by 2. That will change the smoothness by 2, but it will always also change your epsilon requirement, which is kind of captured.
Yeah. So epsilon and L will have the same.
Yeah, epsilon and L, which means that it must appear like that.
This is almost like dimensional analysis.
It is a dimension as that. Sorry, I said it's epsilon and L, right? It's not T.
Epsilon and L.
Of course, yeah. T is something pretty different. T is okay. So what are the limitations of gradient descent? Why only 1 over epsilon? The problem is, this bound here is actually pretty good. It's kind of the best you can do. But this way of choosing a lower bound is actually not very smart. For the following because in some sense you're only using a single hyperplane to construct your lower bound. And you will see that the dual methods we'll talk about have a much smarter strategy to construct these lower bounds. So let me quickly show conceptually what goes wrong with a single hyperplane. So this red line here is your feasible set. So it's a one-dimensional minimization problem. And I query this point. I see this hyperplane. The best lower bound guarantee I have is the minimum of this linear function over the feasible set, which is this value here. This is my current lower bound. Then as I keep querying, my lower bound improves. But notice that because gradient descent wants to keep improving the primal value as well, it's very conservative here, and the lower bound increases very slowly. The smart thing to do to improve the lower bound would be to query a point somewhere here, whose function value might even be higher than this one, but this would allow you to see this kind of hyperplane. And what you do with this kind of hyperplane and this one that you saw before, you average them, and you get a nice flat lower bound to your function. So the point is that if you want better lower bounds, you must be willing to explore other areas of your feasible set where, which may have worse function values, but they give you the gradients you want. All right, so let's turn to dual averaging.
Lorenzo, it seems if you have many hyperplanes and you want to know what's the minimum, like several half space, you want to know what's the minimum of the intersection. That seems like an AP problem just.
Right. So you're not constructing the best possible lower bound. You're just taking the average of them, and you're giving one solution. You could construct a much better lower bounds if you were willing to optimize over the hyperplanes you have, but you're not going to do that. I mean, in some cases, when you have some structure, you can choose to throw away some hyperplanes, for example. But in general, you take the average. Okay, let's talk about dual averaging. So now we have a non-smooth problem. So this kind of problem where the gradient can change abruptly. And we want to produce both an upper bound and a lower bound to our function. A way to make queries, upper bound and a lower bound, that show that we converge quickly. And essentially, whenever we query a point, we get a lower bound, the blue line, and an upper bound just given by the point we queried, the function value. The upper bound, the global upper bound you're going to use is just the average of the function of the points we queried. We could choose the minimum, which is strictly better, but for the analysis we just need the average. So our running upper bound on the optimum value is the average value, the average objective function at the points we queried. What's the lower bound? Well, similar idea, actually completely same idea. We have a linear function for each point we query, so we average them. And we know that their average must be a lower bound to the optimum. So now we have an upper bound and a lower bound. It's a natural thing to do to look at the duality gap, because we want, in some sense, these two quantities to become close to each other. And the duality gap, when you subtract these two quantities, looks like this. So it's a sum over all t's of the gradient applied to x of t minus the optimum. And I'm kind of highlighting this expression because I want to draw a connection to online learning right now. I want to kind of reduce this problem to online learning. And I'm going to claim that this is essentially what's the regret in online learning. Okay? And we'll see why.
Wait, should there be a 1 over t in front of that?
Yes.
Good.
I always, yes. Please, yes.
Isn't the left term the regret?
Raise your hand if you find mistakes. Yeah, there is a 1 over t here because I forgot the averaging. If you imagine this vector here, the gradient, as the loss function at time t, then this will be the loss of my strategy minus the loss of the best expert, of any expert. Let me say that more slowly. So keep this in mind. Let's think about an online setup, where we have an online algorithm, a game, a repeated game, which works this way. We play a point in our feasible set. We are given a gradient. And we don't think of this gradient as a gradient anymore. We think of it as a loss function. And then we suffer this loss, the inner product of the loss function and my point. And we update to a new point, and the game continues. And our goal is, over time, to minimize the average regret, which is the average loss of our algorithm, of our strategy for picking STs, versus the loss of the best point in hindsight, if you were allowed to always to play a point in hindsight, but it has to be a fixed point. So this is a classical notion of regret in online learning. And it's, there are lots of ways to do this. And it should be clear now that if you replace loss function with gradient of the function at xt, this regret and the duality gap are the same thing. So we can solve a non-smooth optimization problem by forgetting that the gradients we are seeing are gradients, throw that information away, just taking them as adversarial linear function, and playing an online regret game. So now I'm going to kind of go one level deeper and explain how these online learning strategies work to minimize regret from an optimization point of view. So ask any questions now if you have any.
Why is externally optical?
So this bound, regret, right? It doesn't have to be. Just take this, x star is whatever minimizes regret. It could be, it doesn't have to be the minimum of the function. I'm just claiming that for all x star, I can provide the upper bound to this quantity.
Can you clarify just a little bit more about why this is duality? Or in what sense this is duality?
In duality gap.
Yeah, so where is the primal and dual pair here that we have?
Well, yeah, maybe I'm thinking of it in terms of having a candidate primal solution, which is the minimum of this point or their average, which has this value, which is guaranteed to have at least this value, and a candidate dual solution, which is the average of these gradients, which I can show as this value. So
what I'm asking is, I totally understand the formulas, but what is this the dual problem of? Or what,
yeah. So
we know what the dual problem is, and in this case, is there some optimization problem that is the dual?
Yes. And we'll see that in the next part. That's how we're going to, exactly how we're going to proceed. I think by going into the online learning, I hope to make it a bit more simple. And then there, I will introduce what the problems are we are working on. All right. So now I'm going to go into online learning. I'm going to quickly review what multiplicative weight updates are, in case you forgot. They are going to be our paradigmatic example of a dual averaging algorithm. So whenever you look at these dual averaging proofs for the first time, think multiplicative weight updates. And then, but I'll give you a proof that never, the proof I give never uses the word, multiplicative. It's completely black, it's more abstract. So I already presented the game. I play a point in a feasible set. I get a linear loss function. I also have some guarantee that these loss functions, there shouldn't be gradient here. These are not too large. This is our same guarantee that comes from the no-smooth optimization. This is also called the width. And I suffer this loss, and I update my point, and I get a new loss, and I continue, and I want to minimize this average regret. Okay. So in the Simplex, the multiplicative weight updates is an algorithm to do this regret minimization when the feasible set is the Simplex. So instead of maintaining a point in an arbitrary convex set, you're maintaining a vector of probabilities. And it's often thought of as a distribution over certain predictors, certain experts. At every iteration, a new set of losses comes in, and your loss is the dot product of the probabilities and the loss vector, which in this case is a nice interpretation as being the expected loss if you actually sampled from your probability. And you keep going. And how does multiplicative weight updates update the probabilities? It keeps some set of weights, and at every iteration, for each expert, so for each dimension of the simplex, you change the weight by a multiplicative factor of 1 minus epsilon to the loss of the expert. And this loss, under some mild assumptions, you can even think about the loss being inside the brackets, 1 minus epsilon loss. But this is actually the more principled way of writing it in some sense. Okay, so what's the intuition here? If your expert suffers a big loss, his weight is going to become tiny. If there is no loss, the weight stays the same. And for now, I think I'm assuming the loss is to be positive. Not necessary. And to recover the probabilities, you just take probabilities proportional to the weights. So these weights are evolving in this multiplicative way. One comment about epsilon, because we'll see that all these dual averaging methods have some sort of parameter. And the role of epsilon is that as epsilon becomes small, the algorithm is more conservative. It doesn't kill off bad experts as fast. As epsilon becomes large, it's more aggressive, and it converges faster to the, it tracks the current best expert much more closely, but will be also less smooth. So even though people, think of it like this usually, I find it more helpful to unravel this recursion, this definition of the weights, and actually think of the weights as 1 minus epsilon to the total loss of the expert up to that point. And so this tells us that in some sense, we are just defining weights that follow this function. At every point in time, our weight is an exponential of the total loss of an expert. Okay, finally, this is the regret bound that you can show. So I'm using the notation L hat for the loss of the algorithm, L star for the best loss in hindsight. And there are these two terms. I want to focus a moment on these two terms. This term here is a startup penalty. It goes down as t increases. It's like just some cost that you pay up front and then goes down. And this term is fixed. It depends on rho and epsilon. So you must make sure that epsilon is small enough to kill rho. And it's kind of just a penalty for being greedy. If you choose epsilon large, which means if you're very conservative, if you are very aggressive, this term is going to be huge. Okay. So this kind of trade-off between, you can make the startup cost huge and pay a small fixed cost, or you can make the startup cost small, but then you pay a big fixed cost. It's something that it's typical of these methods. Okay. So now let me quickly tell you how the proof of this multiplicative weight update works, because the proof of the more general class of dual averaging methods is exactly the same. Same line, the same idea. So the proof is a potential function argument. You have some potential function, which in this case is defined like this. Doesn't really matter what the details are. But what you know is that the potential function is a good lower bound to the loss of the best expert. So now this potential you defined gives you a way of tracking the loss of the best expert. But you also know that the change in potential is related to the loss of your algorithm. So if I suffer a large loss at time t, I know that my potential has to go up. But if my potential goes up, the loss of the best expert must also go up. So this potential really allows us to tie together our algorithm and the best expert. In an ideal world, there will be no epsilon there, and then we would just match the loss of the best expert in average. This is clearly not possible, so we must pay something here. We cannot make the potential function go up by the same amount as our loss. Okay? So let's generalize this proof technique and show dual averaging. So now I'm moving to the simplex, from the simplex to a general convex set. I'm using the same ideas. I want to somehow recreate this potential function argument. And I have two properties I want to have. So I want my potential to lower bound the loss of the best expert. That's like a dual guarantee. But I also want it to track the algorithm's performance. And the most trivial and naive thing you can do is just say, if you want something that tracks the loss of the best expert, just use the loss of the best expert. And so I could define my potential in this way. And it turns out that then the update rule must be that you put kind of all your weight, or that you just pick the best expert, or the best point as your next strategy, as your next play. Okay, so this is a well-defined strategy. It does lower bound, this potential does lower bound the best expert, but it's kind of clear that it cannot track the algorithm's performance, because you may have two experts that are really close in loss. One of them is a bit better. If you put all your weight on the slightly better one, and that better one suffers a huge loss in that iteration, but the other one doesn't suffer any loss, your algorithm has suffered a huge loss, but the best expert hasn't moved. The loss of the best expert hasn't moved. Is that clear? So if that happens, so what that means is that this potential function is not able, it is not tied to the performance of the algorithm. And somehow, even though this may be kind of tricky to see right now, this is really the consequence of a lack of smoothness, which makes sense because we are trying to solve no smooth optimization. And I like to think of it in this way. Instead of the potential as just a single quantity, think of it as a function. It's a function of the current, cumulative loss, all the losses that came through so far. And in some sense, I want to see how this function changes as new losses come in. And it turns out that the gradient of this function is just the argmin. So it's the argmin of the potential, which in this case is the argmin. In this case is the best point, is the current best point. And what I'm saying is that this problem of failing to track the algorithm performance is really due to the fact that this guy, this function of phi of L, is non-smooth. Because I can just change the L, I can just add a tiny loss, and this point can change completely. So the gradient can change completely if I change the input function a bit. Let me be, so this kind of preview, and showing that, dealing with this smoothness is exactly all that you need to fix this problem. So how do we smooth? We know that these guys are non-smooth. How do we smoothen things? How do we smoothen something? There is a technique from optimization called regularization. So you have an optimization problem. It's non-smooth. You add a regularizer. This is called Tikhonov regularization with some parameter lambda. And this regularization has, in some sense, this f has some nice properties that transfer to the whole problem. It could be, it could lead to unique solution. It makes the problem more stable, and other interesting statistical properties. But I guess we are interested simply in making this a smooth function in terms of L. And let me just give you like a 1 minute explanation of what regularization does in our context. So we have this function f of c, which is just the minimum of a linear function over some convex compact set. And its gradient, we said, it's the argmin. And the reason why we were failing is that this function is non-smooth, because if I change c to c prime, even though c and c prime are delta away, the gradient changes completely. So how do I make this smooth? I add a regularizer. And what does the regularizer do? It's a strongly convex function. So do people know what that, let me quickly write what that means. So strongly convex, it's kind of similar to smoothness in the sense that you have a lower bound on your function. You know that it's at least the linear approximation plus a quadratic term. And when I say one strongly convex, I mean 1 here. I think there is actually a typo in this slide. I think I will actually use sigma. So it means so this is for any norm. In the L2 world, this means that the Hessian, if it exists, has all eigenvalues larger than sigma. Okay. So what happens now is that these two lines are not straight anymore, but they are curved, because the function now is strongly convex. And what happens is that when I do the same perturbation again, I go from C to C prime, the minimum point doesn't move so much. Because in some sense, what's happening is that, if I start at C, this is my minimum point. If I look at how well does this point do for the new function, for the blue function, the gradient here cannot be very large, because I only added the delta perturbation. And because my function is strongly convex, if the gradient is delta, I can find the minimum at around this distance from my current point. And here, lambda sigma come in, because this guy f is sigma strongly convex, so multiplied by lambda, this whole term is lambda sigma. This whole term is lambda sigma strongly convex. And if you're familiar with Fenchel-Legendre duality, this is just saying that if, for this kind of expressions, if this regularizer here is sigma strongly convex, this function here must be 1 over sigma smooth. And this is like a very simple thing to prove. Okay. Is this picture clear? This is the whole idea. Once you do this, the proof is done. And why? Because I change my potential function. Now, instead of playing the minimum, instead of the potential is not the minimum loss, but is the regularized minimum loss with some regularizer f. And then I actually claim that once I have this set up, I'm done, because I can first lower bound the loss of the best expert. My best expert, just by the definition of the potential, is lower bounded by the potential, and then there is this term here, which is how big, this regularizer is all very nice. It makes the problem smooth, but it also changes the problem. And so there is a regularization error. So now I still lower bound the best expert, but with some error, which depends on how big my f can be. So I have this step, and how do I show that I track the performance of the algorithm? I use smoothness. Now I have created some smoothness of my potential. So the change in potential is really, I'm thinking about this potential function, how it changes when I add this new loss LT. So this is the cumulative loss now. I add a new term to the loss. And by using smoothness, and now this is a concave function now, so smoothness comes with this sign. You get that this is at least the gradient. So the gradient of my phi, the new term I added to the loss functions, and some quadratic term which depends on the smoothness. But the gradient of my potential function, it's the way I decided to choose my next point. It's the argmin. If you remember, the gradient of my potential is exactly my choice of play at the next round. So what this smoothness equation says is that my change in potential is at least the loss of my expert minus this quantity, which is like a quadratic error. It's a second order term. And it depends on how big the loss function is, which we know it's controlled by the width. Any questions? So this is the proof. Once you get this, it's kind of obvious that you're done because you connected the potential to both the best expert, the best point, and the algorithm. So we showed in one iteration this happens, then just if you telescope, you get that the potential at the end is the total loss of our strategy plus the potential in the beginning minus this quantity, this error that we accumulated. And just by doing some calculation, you get this final bound on the regret. And this bound also has the same terms. There is a startup penalty, which is essentially how much it's the regularization error, how much error you introduced when you inserted this F regularizer. And then there is a term here, which is this, this quadratic term that we paid at every step. So if you put eta large, if you increase the weight of your regularizer, then you pay more in the regularization error, but you pay less at every round because you are more smooth. Okay, so now if you got lost in the proof, you can check in again here because I'm gonna give you an example. So how do we recover multiplicative weight updates from this kind of abstract idea? If you pick F to be the entropy, so if you choose your nest probability distribution by optimizing a trade-off of the expected loss and the entropy, then your update is exactly multiplicative weight updates, and the proof is exactly what I showed you, because you can show that the entropy is a one strongly convex function with respect to the L1 norm. So what I showed you easily, it's an instantiation of what I showed you is multiplicative weight updates. And now the great question is, this is all well and nice, but are there any other useful applications beyond multiplicative weight updates? And the answer is, I think, at least from my point of view, I think within the TCS community, within algorithms specifically, it's recently been more affirmative because we have lots of actually applications of these ideas. For example, we have one paper where we show that different kind of random walks that appear a lot in graph partitioning and in local graph partitioning are just regularized version of the eigenvalue problem. So you want to find a good cut in your graph, and you know that the eigenvalue is a good thing to look at, but it doesn't quite capture the sparsest cut. So maybe you want to, hedge a bit in your computation of the eigenvalue and keep around things that are close to the eigenvalue as well. Or said in another way, the eigenvalue is a very unstable, non-smooth object. If you change one edge in the graph, the eigenvector can change completely. But these random walks, because they are regularized versions of the eigenvalue problem, because they solve these regularized versions of the eigenvalue problems, these are robust. So you can change a bunch of edges in the graph, and your it kernel will not change too much. And that's a great property to have in iterative algorithms, because you want to say, I do an iteration, now I change things a bit, and I can still control what my graph looks like. And another recent, and I think also for me very exciting applications of this is the two-sparsification. So it may not be obvious, but we talked about sparsification, and Nikhil also gave some beautiful lectures in the bootcamp. And we showed there are, so Dan and Nikhil gave spectral sparsifiers that approximate the graph up to 1 plus epsilon with this number of edges using random sampling by effective resistances. And one can show that this is essentially, you can show this result by doing the STP version of multiplicative weight updates, and having, so the edges will be the edges you introduce in the sparsifiers will be the loss functions, and you can just run the same proof in expectation, and you exactly show this result. More precisely, you can actually show the matrix concentration bound used in that result. So this was interesting, but was kind of, people already kind of know the connection between weight updates and dual averaging and concentration bounds. Was more interesting for us was to try to understand also the Batson, Spielman, and Srivastava paper, which gets n over epsilon squared sparsifiers from this dual averaging perspective, from this regularization perspective. And it turns out that we can do that, and there is a completely, there's a regularizer that is kind of strange, but makes sense also based on work done in the machine learning community for learning in the bandit setting. And it turns out that if you choose this regularizer instead of the entropy, you just run this same kind of algorithm, but you put square root p here, then you get exactly the BSS updates, and the same analysis goes through. And actually, if you change this half to fractional values between half and 1, you can recover essentially the same result with a worse constant, but you can compute it faster. So you get this faster way of producing linear size sparsifiers. Okay, so I always go long for this talk. So in the last 2 minutes, let me show you quickly how you get Nesterov out of all of this. It's online.
It's online. Yeah. I'm sorry.
That's fine. So first, concluding concluding dual averaging by stepping back again and going back to the optimization setting. These regret bounds now give us 1 over epsilon squared convergence. How does Nesterov come in? So let me tell you briefly, very briefly, about Nesterov's algorithm. So we are in the smooth setting now, and Nesterov algorithm achieves this kind of guarantee, which is much better than t gradient descent at t here, and now this is t squared. How does it work? It's kind of, it looks mysterious at first, because it's squaring points, and then for every point, it kind of looks at 2 possibilities. It says, oh, I could go to y by taking a gradient step, or I could go to z by taking a dual averaging step. So think of a multiplicative weight update step. I can either do a primal step or a dual step. And essentially, if you have followed, what's really going on is that in some sense, you would, if the gradient is large, you would like to do a gradient step. And if the gradient is small, you would like to do a dual step. But that analysis doesn't work, because in some sense, you cannot mix and match the steps you make here. So what you need to do is something a bit different. What Nesterov does is it picks the next point to be some kind of combination of a gradient and a dual averaging step, and he claims that that's good enough to make progress on both sides. It's not clear why this should work, and the original paper is it's lots of algebraic computations. Now let me try to give you a brief picture of what's going on. So remember the gradient descent analysis, we had this upper bound to the function. So the orange function is the objective function. This one is an upper bound we have at the current point because of smoothness. This is a lower bound that we have been constructing by averaging our hyperplanes. So we are kind of running weight updates and gradient descent at the same time. And this lower bound looks curved because we also are regularizing. We are making it smooth. And what we want to do, in some sense, that at this point we have a notion of gap. We know that the primal is below this point and it's above this point. So we have this duality gap. And in some sense, what happens now is that if I just wanted to do gradient descent, I would pick this point, improve my primal value as much as possible. If I wanted to do dual averaging, I would pick this point, because this would improve my dual variable, my dual problem value as much as possible. And actually, it's possible to write bounds. This is a bit confusing, but you can actually write bounds that show that, if you pick, based on where you pick your next point, you can get this new upper bound and this new lower bound. And then, clearly, instead of picking this point or this point, you should just pick the point which minimizes the next duality gap. And that's exactly what Nesterov does. You can actually you can write these two expressions, and it's just a quadratic minimization problem that tells you, you should pick a very specific point. And this point is always closer to y, because this lower bound is much smoother, while this upper bound it kind of goes up very tightly, so you need to stick close to y to make progress on the duality gap. So the main idea is that you can just think of it as, instead of picking x to optimize the primal or the dual, you optimize the duality gap. So I'm almost done. The last thing I want to say is that, from my point of view, there is a lot of value in understanding these optimization methods beyond their application to graph problems. I think they have applications in as a proof technique as well. For example, I think that our work on understanding BSS is very well motivated as a proof technique. It could have other applications. And I'm also very interested in finding places where you can use these optimization methods in a non-black box way. What I mean is that right now, people just try to find a problem, say it's smooth, and then solve it using Nesterov. Now that I think we have a better understanding within our community of what the building pieces of these algorithms are, we can take problems that do not fall, are not necessarily smooth, but have some nice other property, and still apply these primary dual ideas to them. And an example that I have is recent work that I did with Zaiwan, Allen, Zhu on packing and covering, where if you just apply Nesterov, you cannot get better than 1 over epsilon squared. And there is no way of getting smoothness, because you can actually show that the kind of smoothness you did is not possible. But if you instead really exploit the fact that packing LPs are positive, so the constraint matrix is positive, you can get a different notion of smoothness, which is multiplicative instead of additive. And using that notion, you can apply similar primal dual ideas to get to 1 over epsilon, which was not known before even in the optimization community. So I think there is a lot to be gained by understanding the pieces of these iterative methods and fitting them to different problems we have.
Just which regularizer did you use? I mean, does Nesterov use? You said it for the
BSS?
No, that picture that you had.
That picture, usually Nesterov does things in L2, but here I didn't use a specific regularizer. I just.
Oh, okay. You just said regular. Okay, but if I want to recover Nesterov, is it?
Depends. So if you want to recover the L2 version of Nesterov, you would use the L2 norm squared. Nesterov, in the more general versions of his work, has a generic strongly convex function, which he calls a prox function. That's his name for a regularizer.
So it's just using the strong convexity constant of the function or something.
Yeah. The strong convexity, the inverse of the strong convexity becomes the smoothness of this potential function.
Yeah.